Good morning. Today we'll see about source coding theorem in communication system, and this will be helpful for BE, ECE, CSE, IT student, those who are preparing for communication theory, communication engineering, analog and digital communication, as well as this will be helpful for solving gate questions also. If you get this Shannon Fano coding. See, this is source coding algorithm. We have Shannon Fano, and then next we'll move on to the Huffman coding. A discrete memoryless source. So here we have a discrete memoryless source which has 5 symbols, that is x1, x2, x3, x4, x5 with probabilities. These are the probabilities respectively. Construct a Shannon Fano code for the source and calculate code efficiency. So what we have to do is we have to construct a Shannon Fano code. So the first step in this is we have to write the probabilities in the decreasing order, or we can say that as it should be written as non-increasing order. The number should be written in the decreasing order. See, which is the highest number, that is 0.4, then 0.19, then 0.16, 0.15, 0.15. So already number is in the order, but in the first step we have to write the numbers in the decreasing order, that is in the descending order. So first number should be highest value, then when compared to this, this should be low, compared to this, this should be low. So this is the step 1. Next, the first stage, what we have to do is we have to split this into 2. We have to split this probability into 2 groups, whereas the first group should be, if you add this, the first group should be greater than this number, or else we can split like this. Okay, we have to split this into 2 groups, and the first group should be always represented as 0. The first group should always be represented as 0, and the next groups, that is, this is our next group, this should be represented as 1. Now here we have only 1, so we cannot split this again, so this is over. Here we have 4 ones. Now what we have to do is, again we have to split this into 2 groups. It is not that if we have 4 ones we have to split this into 2 ones. It is not at all like that. The first group should be greater than this second group if you add this, but actually this is not applicable here because this will come more than this. Now we have splitted this into 2 groups. In the first stage we have splitted it into 2 groups. First group will always represent 0. The second group will always represent 1. Now if we have 2 zeros here, then we have to split that, but here we have only 1 0, so leave this as it is. And here we have 4 ones. Now what we have to do, again we have to split this into 2 groups. This is our stage 2. This is our stage 2. Now here we should not carry this 0 here. Since here we have only 1 0, you should not carry this 0 here, because if you carry the 0 here, finally we have to write the complete numbers. So while writing, what happens, if you write this 3, that is 2 zeros or 3 zeros here, so the length will change. So I'll say that later. So leave the 0 as it is. And now what happened, we have split this into 2 groups. The first group should be represented as 0. Second group should be represented as 1. So this is our first group, this is our second group. Now let us move on to stage 3. So in the stage 3, see here we have 0 group, this is our 1 group. Now what we have to do is we have to split this 0 group. So if you split this, the upper part will become 0, lower part will become 1. Similarly, here we have 2 ones. This is called as ones group. Now split this into 2. If you split this into 2, now the upper part will become 0, lower part will become 1. That's it. We cannot split this again because no 2 zeros or no 2 ones are present here. Here we have only single 0, single 1, single 0, single 1. The next stage is we have to write the code word for this. So what is this code word? That is whatever the numbers present here, we have to represent that. That is why I said earlier, if you carry the 0 here, what happens? Now here while writing, we will write 3 zeros. That is wrong. So if you have only 1 0 left alone, then you should not carry the 0 to the stage 2, to the stage 3, because if you carry this to stage 2 and 3, what happens? While writing code word, we used to write this as 3 zeros. So this should not happen. Now here we have 1 0 0, that is 1 0 0. Next 1 0 1, that is 1 0 1. 1 1 0, 1 1 0, 1 1 1, 1 1 1. This is called as code word for this probability. So for this probabilities, this is the code word. Then the next one, finally we have number of bits. So what is the number of bits? So how can we write this number of bits? That is how many numbers here we have, the length. We have to represent this length, that is 1. And here we have 3. Here we have 3. 3 bits, 3 bits. That's it. This is the Shannon Fano coding. So what we did is just first step, we have to write the probability in the descending order. So after that, we have to split it into 2 groups. The top group is said to be, that is the group 1 is said to be 0 group, and group 2 is said to be 1 group. So if we have 1 0, just leave as it is. Now let us move on to the 1 group. Again we have to split this 1 group into 2 groups, whereas the group above this group is said to be 0 group, and the bottom group is said to be 1 group. So 0 1. Again we have 2 0 2 1. Again split this. The top above this line is said to be 0 group, below this line is said to be 1 group. Same way, above this line is said to be 0 group, below this line is said to be 1 group. That's it. We cannot split it again. So let us stop here. Now we have to write the code word. So what is a code word? So we have to write these numbers as the code word. So 0, 1 0 0, 1 0 1, 1 1 0, 1 1 1. Then number of bits. How can we write the number of bits? So how many length? So how many bits are present? That represents the number of bits. So here we have only 1 bit, 3 3 3 3. That's it. And now what we have to do is, we have to find the entropy of this. Entropy. So how can we find this entropy? So entropy is written as H. Entropy is represented as H, which is equal to summation K is equal to 1 to M Pk log base to 1 divided by Pk. This is the formula for entropy. So entropy H is equal to summation K is equal to 1 to M Pk log base to 1 by Pk. Now what we have to do is, we have to substitute this values in this equation so that we can find the entropy value. Now what is present here? That is entropy H is equal to Pk. Pk represents this probability, that is 0.4 log base to 1 divided by 0.4. This Pk represents probability, plus 0.19 log base to 1 divided by 0.9 plus 0.16 log base to 1 divided by 0.16 plus 0.15 log base to 1 divided by 0.15 plus 0.15 log base to 1 divided by 0.15. Now what we can do is, since it is in the log base 2, but in Calc we can do log base 10 easily, so we can change this log base 2 to log base 10. So how can we change this? Log base 10, 1 divided by 0.4 divided by log base 10 2. Now if you divide this by log base 10 2, this will become log base 10, that is, if this base 2 will be converted to log base 10. So we can write this as log base 10 1 divided by 0.9, that is 0.19 divided by log base 2 log base 10 2, plus similarly we have to write this everything. So after writing this, so what we did is, we have converted this Pk, that is log base 2 to log base 10. Now we have to calculate this, that is 0.4. Calculate this. because this calculation takes time. So log base 10, 1 by 0.5 log base 10. So finally h is equal to 2.2281 bits per message. So this is our answer for this H, entropy. But what is asked in the question is calculate the code efficiency. Now how can we calculate the code efficiency? That is, we can calculate the code efficiency, that is average number of bits per message, that is n bar. So this is given as, which is equal to summation k is equal to 0 to L minus 1, that is length L minus 1 into pk into nk. Now what is this pk nk? We know that pk is probability. Now what is n? That n is this length. So here we have written number of bits, and this number of bits represents length. Now here we have 0.4 into 1 plus 0.19 into, that is 0.19 into 3 plus 0.16 into 3 plus 0.15 into 3 plus 0.15 into 3, that is our average number of bits, plus 0.19 into 3 plus 0.16 into 3 plus 0.15 into 3 plus 0.15 into 3. Therefore we will have 1 minute, it takes time for calculating, which is equal to 2.35. So this is our n bar. Why we are calculating this n bar? Because we have asked this find code efficiency. This code efficiency can be calculated eta, which is equal to h divided by n bar. Now what is h? H is equal to 2.2281 divided by 2.35, that's it. So 2.2281 divided by 0.35 is equal to 0.948. This is the answer. So this is how we have to find the answer for this Shannon Fano coding. This is code efficiency, and here we have n bar, and here we have h is equal to entropy. So suppose if you are asked to find only entropy, then it is sufficient. This h, we have to stop up to h. Then if we are asking for code efficiency, then we have to find this h by n bar. So what is this h? Entropy. N bar is average number of bits, and this can be calculated by this formula. So this is how we have to find Shannon Fano coding. Now let us move on to the next problem. A discrete memoryless source has the following probabilities. Now see here, a discrete memoryless source has the following probabilities: 0.07, 0.08, 4, 26, 14, 09, 07, 025 respectively. Construct a Shannon Fano code from the source. Calculate the code efficiency in the same way. So what is the first step? First step is we have to write the probability in the non-decreasing order. We can say this in the non-increasing order. We can see this in the descending order. So which is the highest number here? That is 0.26. And then the next value is 0.25. Then the next value is 0.14. Then the next value is 0.09. And the next value is 0.08. And the next value is 0.07, but we have 2 times, so 0.07, and finally that is 0.04. So let us check 1 2 3 4 5 6 7 8. So 1 2 3, okay, 8 values are there. So first step is we have to write the numbers in the decreasing order, that is we have to write the numbers in the descending order. So what is our stage 1? So what we have to do in the stage 1, stage 2, stage 3. So in the stage 1, what we have to do is we have to split this into 2 groups. So the top above this line is said to be 0 group, and below line is said to be 1 group. That's it. And in the stage 2, so what we have to do in the stage 2? So in the stage 2, now again here we have 2 zeros. So previously in the previous problem we had only 1 zero, but now we have 2 zeros. So now split this into 2. After this, let us split this into 2 groups. and now here it is 0 group, 1 group. So above this line is 0, below this line is 1. And now here we have second group, 1 group. Now we have to split this 1 group, and listen, remember, you should not combine these two groups. This is called as 0 group, this is called as 1 group. So you should not combine these two groups, and you should not write zeros or ones. The 0 group should be grouped separately. Likewise 1 group should be grouped separately. Now after splitting this, now what we have to write is above this line is 0, below this line is 1. Then the next one is, let us move on to stage 3. So in the stage 3, you should not carry this because this is over. The stage 3, what we have to do, this is 0 group and this is 1 group. So 0 should be split like this, and the line above this is 0, line below this is 1. And here we have 4 zeros. Now let us split this into 2. And the line above this is 0. The line below this is 1. Then we have stage 4. Now we should not take this here to the stage 4 because 0, 1 is over. And now here we have only 0 group, 1 group. So now you split this into 2 and you split this into 2. This is 0 group, this is 1 group. So the line above this is 0. The line below this is 1. The line above this is 0. Line below this is 1. Now what is the next thing? We have to write the code word. So what is the code word here? 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1, 1. So this is code word. And what is the next step? Next is we have to write the number of bits. So what is the number of bits here? 2, 2. Here we have 3, 3. And then next one is 4, 4. 1, 2, 3, 4, 4. So this is how we have to write the Shannon Fano code. So first is split this into 2 groups. The above group represents 0 group and the below group represents 1 group. And you should not combine this 0 and 1. This is 0 group, this is 1 group. Again split this 0 group so that we will get 0, 1. Now split this 1 group. There we will get 0 group and the line below this will be 1 group. Again now you should not continue this because 0 and 1 is over. Now here we have 0 group. Now what happens? Split this 0, 1. Now here we have 4 ones. Split this. So 0, 0, 1, 1. Now you should not carry this. Here we have 2, 0, 2, 1. Now split this 0, 1. Split this 0, 1. That's it. Now we have to write the code word number of bits. And what is the next step? Next step is we have to find the entropy H. Now, we cannot find here. We have to find entropy. So as previous problem, same, entropy H. The remaining everything will be like previous problem. So entropy H is equal to. So now refer your previous problem. What we have written? Entropy H is equal to. So here we have written, just a minute. Entropy H is equal to summation. K is equal to 1 to m p k log base to 1 by pk. So we can write directly, which is equal to, what is this pk? That is 0.26 log. Now we know how to write base 10, 1 divided by 0.26, the whole divided by log base 10, 2 plus. Now you complete this entropy. 1 minute. Listen. This is how we have to write this entropy. Just expand the equation. But what we did is, instead of log base 2, I have written log base 10 directly, because in the previous problem I said how to convert this log base 2 to log base 10. So that is 0.26. That is our probability. So 0.26 log base 10, 1 divided by 0.26 divided by log base 10 2. Then we have 0.25 probability, 0.14, 0.09, 0.08, 0.07, 0.07, 0.04. Now what we have to find? Entropy H is equal to. So now we have to find entropy H is equal to. Now use calculator and find what is the value of H. H is equal to 0.505 plus 0.5 plus 0.397 plus 0.312 plus 0.29 plus 0.268 plus 0.268 plus 0.185. Therefore H is equal to 2.725. This is our entropy H. So entropy H is equal to, now what is the next step? We have to find n bar. So n bar, which is equal to, we know that summation k is equal to 0 to L minus 1 pk into nk, and we know how to write this, that is 0.26 into, what is our probability? 0.26 into, just listen, 0.26 into 2. So 0.26 into 2 plus 0.25 into 2. I'll do calculation straight away. 0.25 into 2, because we know how to write this. So I don't want to waste time, just listen. 0.25 into 2 plus 0.25, 0.14, 0.09, 0.08, 0.07 into 4, 0.07 into 4, 0.04 into 4. Therefore, n bar is equal to 2.75. Now, what is code efficiency? Eta is equal to h divided by n bar. So, it is equal to 2.725 divided by 2.75. Therefore, which is equal to 0.99. So this is our code efficiency. So this is how we have to find. This is n bar, and listen, I have not written this, just continuation, you have to write this. This is h bar efficiency, entropy, n bar, and this is code efficiency. But to remember, always the entropy, that is always our code efficiency will be less than this one, and always our code entropy will be like this. Remember, efficiency will be always less than 1. So you must remember this. Code efficiency will be always less than 1. So this is how we have to do this Shannon Fano coding. Hope you remember and you understand this, and we will see Huffman coding in the next video. Thank you.